Hello and welcome back to my tutorials on R. Today I'm going to show you how to use three basic functions in R to fit statistical models. These three functions are the LM function, the GLM function and the GLS function. And after having seen this video, I hope you will be able to work more easily with these functions. So in this video I'll show LM. This is the traditional workhorse to fit linear statistical models and to perform traditional linear regression analysis. When you have normally distributed errors and constant variance. Now in many cases errors will not be normally distributed and the variance will not be constant. There are two ways to cure that. First is to use GLM, which fits a generalized linear model with non-normal errors and non-constant variance. And finally, with the GLS function, fits a generalized least squares model, GLS, generalized least squares, also with the same properties as the GLM, and especially useful if you have correlated errors or if you have spatial or temporal trends in your data, patterns or trends. Now I don't want to bother you too long with these theoretical introductions. Let's directly use R in order to fit LM, GLM and GLS models. Okay, here we are. This is R. I'm now opening a new script window as usual and arranging the windows vertically. And we're going to use again the air quality dataset. So we use the air quality dataset, and before we start modeling, it's always good to produce a graph of what we want to do. There are two types of things we want to do. The first thing will be to plot ozone concentration against an explanatory variable. So plot ozone as a function of wind, for example, and the dataset is air quality. Okay, we do that, and we get the plot that you may have seen already. Ozone concentration as a function of wind speed in miles per hour. Alright, so we see there is pattern in the data. There might be some nonlinearity, but we don't account for that in this session. Okay, now let's fit the linear model. We've done it already. We don't need to spend too much time with it here. Model 1 equals LM, brackets opened, ozone as a function of wind, and the dataset will be air quality. And if we plot this model, we can see that, wow, there is nonlinearity and non-constant variance. So the model clearly is wrong. And we close all these windows now. We just briefly look at the coefficients of that model, the intercept and the slope. Now let's just assume that we would like to predict from that model for a particular pair of values. Let's say we want to predict for a wind speed of 20 and, well, let's say of 19 and 20 miles per hour. Let's do that quickly. We have the intercept here, so we have the wind speed 1 will be coef of model 1. Which one do we need? The first one. This is giving us the intercept, just showing it to you here. So the first one here plus coef model 1 and the second one times 19 miles per hour. So this is the first wind speed here, and let's produce the other one for 20 miles per hour also. Call it wind 2. And let's have a look at these ones here. Wind 1 is going to be, actually, sorry, it's not, should be called wind 1, it should be called ozone 1 and ozone 2. Okay. Let's just run these lines again. So the first ozone concentration is predicted to be -8, and the second one is predicted to be -14. That's strange, isn't it? There's something wrong. Let's look at the plot again here. So for a wind speed of more than 19 or 20, the model actually predicts negative ozone concentrations. That's not what we want, is it? So we would like to have something different here. We would like to force the model to be nonlinear in some way. And let's just assume that the ozone concentration has been measured as a count process. It's not true in this case, but in order to have one dataset with which we can play through all these scenarios, I think it's a nice assumption. So let's produce another model. Model 2 will be now a GLM of ozone as a function of wind. Dataset will be air quality. And the family equals Poisson. Now what does this model do? Let's just press Ctrl R here, and let's look at the coefficients of model 2. Now these are wildly different from the coefficients that we obtained before. The intercept is now 5 and the slope is -0.14. So where does this come from? Well, it comes from the fact that we are fitting a so-called Poisson generalized linear model, and this Poisson generalized linear model completely works in a different way when it comes to the parameters. So let's look at that graphically in our Notepad application here. So the linear model, you may be very familiar with that. The LM function fits the following. So for an LM model, you have y equals a plus bx plus errors. So it's a completely additive model with two parameters here, and we know that these parameters were around, let's look back at R, they were around plus 96 and -5. Now the GLM does something different. The GLM fits the log of y equals a plus bx plus errors, or put it differently, it fits y equals e to the power of a plus bx plus the errors. Now, the parameters we get when we look at the model output are these ones up here, a plus bx, and this can be rewritten as follows: y equals e to the power of a times e to the power of bx plus the errors. This shows that the GLM model on the original scale of the response variable is multiplicative. But still, it is linear in the parameters in a sense that what we put up here is the same as what we wrote up here for the LM model. This thing that I just circled here is called the linear predictor. What you can see is that the parameters in the generalized linear model are exponents of an e function here. And if you want to transform these back to the original scale, you have to take the log of this whole expression up here, this a plus bx. Okay, so you know now, even if you haven't understood it completely, you may know that a GLM model somehow uses exponential functions and logarithms internally. Now let's see what that all means. Let's assume that we want to predict, again, our two ozone concentrations. Okay, let's copy the code from above, but be sure to use model 2 now instead of model 1, because we want to predict from the GLM model. And there's something very interesting to be learned from what we are doing right now. So let's call this first ozone concentration ozone1.glm, and the second also ozone2.glm. Now this is the predicted ozone concentration for a wind speed of 19 miles per hour. And the next one will be the predicted ozone concentration for a wind speed of 20 miles per hour. What we need to do now is we need to exponentiate this whole expression here. E to the power of this whole expression here. And the same for ozone2.glm. We type e to the power of this whole expression here. Okay, now we have ozone1.glm, ozone2.glm. Let's see what we get. We have a predicted concentration of 9.49, and for the second one, ozone2.glm, 8. Let's look at the plot again. Plot ozone versus wind. We are at 19 and 20. So let's see what we have here. Could be quite reasonable to have concentrations in the positive range here, just above 0 ozone concentration. Okay, now here comes the interesting part. What happens if we divide ozone 2 by ozone 1? Ozone2.glm divided by ozone1.glm. What do we get? We get a value of 0.86. Okay. Now let's see if that matches anything that we know already. Let's use the slope coefficient of model 2, e to the power of coef model 2, and we want to have the second coefficient here. What is e to the power? What is this coefficient? It's minus 0.14, just to remind ourselves. So it's e to the power of this whole thing here. Okay, what do we get here? That's a nice question, isn't it? We get 0.86 again. 0.86. So we found something really important now. The slope in a generalized linear model fit by Poisson errors, this slope here, if we exponentiate it, the e to the power of this slope here gives us the proportional change in ozone concentration if we change wind speed by 1 unit. We change wind speed from 19 to 20, and ozone concentration in that case goes down by a factor of minus e to the power of minus 0.14. And this is so important that I would recommend to really note it down on paper. So that's what we're doing now. So in a generalized linear model, an individual slope gives an estimate of the multiplicative change in the response variable for a 1 unit change in the corresponding explanatory variable. Okay, now our example, e.g. the slope b from a GLM is, let's go back to what it was, minus 0.14, minus 0.14. Then it follows for a 1 unit change in wind speed, ozone concentration decreases, ozone concentration decreases e to the power of minus 0.14 fold. That's very important. It will help you interpreting the output from generalized linear models and even from more complex generalized linear models. For a 1 unit change in wind speed, ozone concentration decreases e to the power of minus 0.14 fold. In our case, and in general, it's e to the power of minus b. So when you see the output from a GLM like this one here, if you just easily take e to the power of this coefficient here, you know that for a 1 unit change in wind speed, you get that kind of decrease in the response variable. Isn't that fascinating? All right, so far for now with the GLM models. And I would like to show you something else, which is generalized least squares models. I promised you to show you more than 2 modeling approaches with the same dataset. So model 3 gets GLS ozone as a function of wind speed from the air quality dataset. Now, in order to call the GLS function, we need to load the LLME library. Okay, and we just fit this model here, and I promise you, you will get an error message here because there are missing values in the object. So where could these missing values come from? Let's look at the air quality dataset, and we produce a summary of air quality $ozone. Aha, there we go. In the ozone variable, this is the minimum, this is the median, and so on. And here, back here, we see there's 37 missing values, so-called NAs, for not available. There are 37 of these values in the dataset. So what we need to do in order to be able to fit our GLS model here is that we need to state NA, NA.action equals NA.exclude. Okay, that's the first thing we want to do. The second thing is I would like to draw your attention to the dataset we're working with. Let's just look at the head of the air quality dataset. What does it say? This is a short summary of the first 6 lines of the air quality dataset. It shows us there is the ozone concentration, there is solar radiation, wind, temperature, and there is something else in here, month and day. Now, what do we do with that? Let's see if we can create a date out of it, and let's look at the help file for the air quality dataset, just very briefly. Okay, the help file shows us that these measurements have been taken in the years 1973. Okay, let's incorporate that information and produce a date variable from month, day, and year. So let's use the paste command. Paste 1973, comma, air quality $month, air quality $day, and sep equals a dash. What do we get here? We get a character object consisting of the year, the month, and the day. And if we say as.date of that object, depending on your system, you see that this has been successfully converted to a date object. So we have the months and the days of the year 1973 now. We use this information in order to create a new column in the air quality dataset. Let's produce a plot here using the lattice library. Library lattice. Okay. XY plot. And we use the ozone concentration as a function of date. Dataset is air quality. Okay, there we go. We see that the x-axis has been properly labeled now with month names even here. And we see there is a temporal structure in our data that we had not accounted for beforehand. Now let us incorporate the information on this temporal trend in our data into our model. Copy the code from above here, call it model 4, is a GLS ozone wind times date air quality. Let's say we would like to see whether there is temporal autocorrelation in that model. Let's try it out. Plot ACF model 4. You can see that this produces an error. There is nothing in this plot. So where could that come from? It comes from the fact that we have missing values in our data. So before we can look at temporal autocorrelation, we need to create a new dataset called air2 equals subset of air quality. And we want to subset air quality by the complete cases of ozone. Okay, now we've created a new dataset. Okay, now we've created a new dataset called air2, and we use this dataset now in our modeling. This will be model 5. Is a GLS, and we don't need this one here anymore. We just need to tell R that we use the air2 dataset now. Model 5. Plot ACF model 5. Form equals tilde date. There we go. So there is some pattern in here in the residuals of the model. We don't know whether that autocorrelation is significant. In order to produce significance lines, we can say alpha equals 0.05 here, and be sure to put the alpha after that bracket here. Okay? Now this is the plot we get. There are some indications of some days actually here. Some individual days for which there is significant or marginally significant positive autocorrelation in the data. The first one here is always set to 1 by default, at lag 0 here. Okay, this shows that there is some temporal pattern in the data. We know that already. So in order to account for that, and this is one of the strengths of the GLS function, in order to account for that, we just update model 5 here, call it model 6. Model 6 is update model 5 correlation equals core AR1 brackets. Okay, and now we just need to compare these two models, model 5 and model 6, with one another using the AICC function from the Moomin library multi-model inference. Be sure to type this correctly here. Let's use the AICC of model 5 and model 6. And be sure to have installed this package also. And we can see that the AICC goes down slightly. So the model 6 is a bit better in explaining the data than model 5. Now let's look at the summary of model 6. And then we are done with these analysis already. Summary model 6 shows us the following. It shows us the AIC, which is different from the AICC because AICC is corrected for small sample sizes. It shows us also the BIC, the Bayesian Information Criterion, the log likelihood. And it shows us also that we've incorporated an autoregressive correlation structure of order 1 here with a parameter estimate here. And these are the coefficients we get. It's a bit more complicated now because there's an interaction term, there is date, there is wind in here. We get correlation of the coefficients down here. They are basically highly correlated because of the presence of the interaction term here, and also because there seems to be a strong relationship between wind speed and date. We get the residuals of the model as a summary here, and we see a summary of the degrees of freedom, which is basically the amounts of individual measurements that have been taken. Okay, to summarize quickly what we've done today is we have used LM, GLM, and GLS in order to analyze a dataset in R, and we have seen the following. We have seen that LM can be used for traditional linear models. We have seen that GLM can be used for Poisson or count data. We've done that with the ozone response variable, knowing that it isn't really a count variable, but nevertheless restricted to be positive and coming in integer batches. And we have the GLS function that allows us to flexibly incorporate temporal autocorrelation into our statistical analysis. And there is more to that. There is, for example, the GAM function for generalized additive models. That's something for the future. With this session, I just wanted to introduce you quickly to these three functions, and you get a feeling for the way you can do your statistical analysis. Okay, I hope to see you again soon in the next sessions with R here. You can see that we are taking up speed now and reaching a bit more complex topics. Stay connected, and I hope to see you soon later on. Bye-bye.